Well, in order to find the unit that we're going to use for this, what we're going to do is rearrange the equation and solve for C. So, let's rearrange the equation and solve for C. What would it be? Yes. I'm guessing this is what you meant. Okay, good. Yeah, that's exactly it. Okay? So if we do that, remember our Q's are measured in what units? Joules. Our M's, our masses, are measured in grams. And what is our temperatures measured in? Degrees Celsius. Does anything cancel? No. So what's our unit for heat capacity? Per gram degree Celsius. Okay? So there we go. The unit for heat capacity is joules per gram degree Celsius. How much energy is a joule? Now, you guys have worked with joules before, probably in physical science. You guys did some kinetic energy calculations, some gravitational potential energy calculations, probably. Your units were in joules. You came up with these numbers, but I'm not sure if you ever had a discussion about how big is a joule. Has that ever come up before? Okay, well, I have a couple of different analogies for you there, or actually some fun facts if you care. What's another unit of energy that you might be actually more familiar with on a day-to-day basis? What's that? Calorie. Exactly. You guys deal with calories all the time, right? Sort of. We'll get to that in a second. And does anybody have like a food item with them that has like the nutritional label on it? Water. Can you look up how many calories are in that, please? Okay. Does anyone have a food? Excellent. Great. So what is the caloric value? I'm sorry, what? 180 what? Calories. Are you sure? How is that word calorie spelled? No. Look carefully. Matt, can you help him out a little bit? Be more specific. And how is the word calorie spelled? Be more specific. Oh, capital C. I'm sorry, what's that? You may have. It's possible you may have. So let's do this. Here is a list of substances. What types of substances are these? You guys may not know all these symbols yet. You will. Aluminum, zinc, lead, nickel, copper. Okay, we'll trust me, we're going to spend a lot of time on that stuff. Okay. Anyway, look at these heat capacities. The numbers don't mean a lot to you. So let me throw up another really familiar substance up here. What do you notice about this heat capacity relative to all of these? A lot higher. Would you agree? Okay, and that goes along with what we were saying yesterday with boiling water. The pan is going to be too hot to touch even after a couple of minutes, yet the water you are going to be able to touch because its heat capacity is greater. It's able to absorb a lot of energy before its temperature starts changing. Okay, and this should point that out to you. However, there is a nice little thing here that I want to point out. 4.184 joules is equivalent to 1 calorie. Now, I do want you to notice a difference there. That means a joule is, what is the size of a joule relative to a calorie? It's 4 times small, a little over 4 times smaller, would you agree? A joule is a smaller unit of energy than a calorie. You do not have to write this next thing down, but I do want to tell you what the definition of a calorie is. Excuse me, pardon me, excuse me. And again, unless you desperately want to, you do not have to write this down, but the definition of a calorie is the amount of energy required to raise the temperature of 1 gram of water. Now, does anybody know the density of water? 1 gram per milliliter. So when I say 1 gram of water, I'm also referring to 1 milliliter of water, right? A calorie is the amount of energy required to raise the temperature of 1 milliliter of water, that right there, by 1 degree Celsius. Do you think that's a lot of energy? How could I relatively easily warm that water up by 1 degree Celsius? Holding it in your hand for a little while. Do you think that would probably do it? Shake it up a little bit to kind of distribute the energy, but it wouldn't take long to do that. Okay, so a calorie is a pretty small unit of energy. Would you agree? Yet a joule is, as Luke was saying earlier, a little over 4 times smaller than that. So a joule is actually a pretty tiny piece of energy. Okay. One other thing I want you to notice. Notice what I wrote here. And notice what I wrote here. Lowercase c. Capital C. What's the difference? This is actually a kilocalorie. Remember, a kilo is 1,000. Right? Prefix kilo means 1,000. So, this is actually how many of these? 180,000 calories. Okay? Now, here's a fun little thing. Now, this used to be a big deal. This used to be something that people knew and understood pretty well, but nobody does it. You guys are like way too healthy now, which is not a bad thing. But does anyone happen to know how many calories are in a Big Mac? Oh, you know this.
Is there? I'm pretty sure it is 5.
Yeah, it's about that. Oh, this ought to be fun then. Okay, so 540 right? Calories. Let's find out how many joules that is. Now, watch this. We have to convert to calories first, and we know there's 1,000 calories in 1 calorie, which is called a kilocalorie. Okay, so all the ingredients that you guys read, all the caloric values, are all in kilocalories. And then what are we going to do? Yeah, by putting what in the numerator? How many? 4.184. Look at you guys go. You are so good at this now. So, how many joules of energy are in a Big Mac? Well, if you could do a quick estimate, and find out that it's a little over 2 million. Did you get it? Okay, look, because 4 times 500 is 2,000, over 2,000, but 2,000, right? And 2,000 times 1,000 is 2 million. So we're talking a Big Mac has over 2 million. 259. Oh, sorry about that. We'll just stop there. Yeah. 2,259,000 joules of energy in a Big Mac. How much energy is a joule? It's a pretty small unit of energy. Okay. In fact, most of the times we deal with kilojoules because it just makes the numbers easier to deal with. Okay? So that'd be 2,200 kilojoules. Anyway, just thought I'd have that conversation with you to give you a sense of why a lot of the times when we're doing energy calculations that our values for our joules are going to be relatively higher than what you think are used to dealing with. For example, our density calculations were in things like, what, 2, I think the biggest one we had was 10 or 11 for our densities, right? But when we're doing our energy calculations, we're going to be in the thousands and above. So just keep that in mind as we're going through this stuff. Okay. As you can see, different metals have different heat capacities. Did I ask you yesterday what your pots and pans were made out of? Did that come up? Wood? Who said wood? What kind of metals are your cast iron? Your like pot that you heat up your water? Aluminum a lot of times, stainless steel, right? Does anyone have copper utensils at home? Really? You must live in Olentangy then. You must live in New Albany. How many of you have copper utensils at home? Not very many do. Why not? Yeah, it's real expensive. Now, here's a way to get around that now. How many of you have some utensils that have a copper bottom, but the rest of it's like aluminum or, okay, now that's a little bit less expensive, okay? Because really, where is the heat source? At the bottom, right? So we would like the metal that is closest to the heat source to have a lower heat capacity. And if you look here, copper, other than lead, has about the lowest heat capacity there. Would you agree? Do you know what the melting point of lead is? Yeah, I was just going to say. Has anyone, it's possible, has anyone melted lead before? Have you? Okay. What for, just out of curiosity? Huh? Yeah. You just found some lead and decided to melt it? Has anyone else melted? There's a reason why you might melt lead. No one else has? Okay. Like if you're making your own ammunition and stuff, you would melt your own lead. People do that. So, okay. Anyway. Lead has a pretty low melting point. Your stovetop would be probably, if you turn it on high, enough to melt the lead. So whoever asked that, was that you? No, I was. Who is asking? Oh, about why we don't use lead? Okay, doesn't matter. Somebody asked that question. That's why. All right. So if you make it out of the rest of your pan or pot or whatever out of aluminum, which is relatively cheap, okay, but then put a copper bottom on it, now you're kind of getting the best of both worlds, where the heat transfer process is happening where the copper is, yet you're not spending all kinds of money on that. So, one other analogy, because I like you guys to use the ideas that we're learning and try to, as much as possible, transfer to that things that you've actually observed before. It doesn't work, it doesn't happen all the time, but this one's a really good one. Does anyone have carpet in their bedroom? Anyone? Probably almost all of you. Okay. How many of you that had your hands up that have carpet in your bedroom, or at least the hallway leading to your bathroom? How many have a tile bathroom floor? Okay. So here we are. And let's imagine we're in the middle of like January or February. It's cold out. Your house is probably kind of chilly, right? You wake up in the morning. You put your feet on the floor, which is carpeted. What do your feet feel like as soon as they hit the floor? When you put your feet on the carpet? You don't really notice. And you guys all gave exactly the response I was expecting. You kind of looked at me like, I don't know, it feels like I'm stepping on carpet. Okay. So you don't really notice anything temperature-wise, right? And you walk down to the bathroom, and you step on the tile floor. Do you enjoy that? Why not? Because it's cold, right? How many of you would notice a difference stepping off from the carpet to the tile floor? So you're saying that the tile floor that has been inside your house all night long is at a different temperature than the carpet that has been in your house all night long. Are they at different temperatures? They are not. They are at exactly the same temperature. Then why does it feel so cold? Why do they have this? Why does the tile feel colder? Think this through. Don't just blurt out an answer.
The tile has a higher heat.
Meaning what? Than the carpet does. So, as soon as your foot hits the carpet, which has a relatively low heat capacity, its temperature changes pretty quickly to be whatever your temperature is. But the tile, on the other hand, has a high heat capacity. As you step on that tile, it takes a long time for its energy, for it to come to the same or similar temperature as you, so it's sucking all this energy out of you. That's why your foot feels cold. Now, eventually it doesn't warm up, but you have to stand there for a little while. Would you agree? Yeah. So there's an application of what you guys may have noticed before. Okay. I think you guys understand the concept of heat capacity pretty well. You get this stuff. Now it's a matter of practicing some calculations with this. You are a group that recently has done these calculations, is that right? Could you pull out that assignment and your work that you attempted to do for that assignment? Oh, hi, everybody say hi to Mr. Strangis.
Morning, everybody. Morning. Nice for that blue ribbon presentation. They want to put something up on the floor.
Okay, here's what I'm going to do. We're going to walk over here because currently this video is going to go out to the world here in a second.
Oh.
Yeah.
Okay.
Because I'm
What are you video to do?
So what were you saying? All right. Hold on a second. Okay, let's see if these are it, and they should be. Okay, now, you were probably not incredibly successful because you did this all on your own, right? However, this is what should be happening here. So I'll let you guys kind of peruse what you did. I'm going to give you some more opportunities to practice this. I've got some other worksheets, okay? But what I would like you to do is look at what you did, look at the information that we have up here. Now I want to point something out. Here is this equation, which is what I would consider to be the standard equation that we can rearrange and solve for anything we want to. And those are probably going to be the two main equations that we end up using. Can I scroll past number 1? And I'll throw these up on Canvas for you guys to look at too, but
Can you explain the HG?
can I explain what?
The HG part in number 1.
The HG part in number 1. I don't know what the wait, here we go. You mean what the symbol HG, why that's there? Oh, because that's the symbol for Mercury. I know, you didn't know that.
Yes.
Very similar to these. You're going to know these really soon. Okay. You're going to be asked to know those really soon. What's that?
We should start putting those lists.
If you know it. You can write it out if you want. You can just write out Mercury if you want. I like to write out what everything stands for because, as you're going to find out really soon when we start doing a lab, we're going to have temperatures of like 3 different things. We're going to have masses of 2 or 3 different things, and it's much easier to label what they represent so you don't get confused when you're doing your calculations. That's that whole labeling thing we talked about earlier. Okay, can I get past number 1? What about number 2? Can I get past number 2? Don't all of you nod your heads at once because it creates enough wind that it blows me over. There are 3 and 4. Hi. You may. I think the flask is over there. Is it over there? Number 3 is kind of tough because you're solving for a different, you're solving for something embedded within the delta T. Remember we saw that change in temperature meant final minus initial, right? So basically I had to isolate, in that case, I believe the TI. That's just algebra. I mean, you just do algebra. Algebra. You guys do that in your head, right? I do highly recommend, and you've heard me say this before, that you rearrange the equation first before you start plugging numbers in, because otherwise you can imagine how ugly that would have gotten if you'd started moving numbers all over the place. And then the more times you write things down, the more chances you have to make mistakes. So always rearrange the equation first, then plug the numbers in. Hence the phrase, plug and chug. You guys have heard this before, right? I'm going to go past number 3. And once again, this is going to end up on Canvas if you're not able to keep up. Pardon? and 5 and 6. Now, let's talk about 5 and 6 because this is where our lab that we're going to do is going to come into play here. I don't know. I feel like 15 minutes. Where am I? 12? Okay. All right, so what we're going to do is we're going to have a big beaker of water. That we're going to heat up. Using the burner. And then we're going to suspend in that a big test tube. And in that test tube, we're going to put a bunch of metal. Same kind of metals we use for the density lab. We're going to heat that water up until it starts boiling. At approximately what temperature will the water start boiling? Pardon me? 100 degrees Celsius, very good. Really close to 100 degrees Celsius. It's probably not going to be exactly 100 degrees Celsius. In fact, it's probably going to be a little bit less than 100 degrees Celsius. Have we had that discussion yet about why that might be true? Okay, I'll mention that. I don't want to do it right now because we don't have very much time. But let's say the temperature ends up being 98.4 degrees Celsius. If I keep that metal in the test tube in there for, let's say, 10 minutes, what temperature do you think that metal will become? About 98.4 degrees Celsius. Would you guys agree with that? At some point in time, it's going to come to the same temperature as the water bath. Okay? Off to the side, I'm going to have some styrofoam cups. In fact, there's going to be 2 of them that are stacked within each other. Okay? We'll get into why styrofoam is a very good insulator later, but what is styrofoam made mostly of? It turns out air. That's why it's a really good insulator. We'll have that discussion later also. We're going to put some water in there. And in fact, that water is going to have a mass of about 100 grams. I'll say 99.24 grams of water. Okay? We're going to measure its temperature. Now, it's going to come out of the sink, so therefore its temperature is probably going to be something around room temperature, which is, let's call it 23 degrees Celsius. Remember we said 68 degrees is 20? We're a little bit above that, so we'll say 23. That might be a little warm, but we'll let it go, okay? Then, what we're going to do, once this has reached the same temperature as the water after X amount of time, we're going to take that metal and quickly transfer it to this water. What's going to happen to the temperature of this water? It's going to go up. Why? We just put something that is at a higher temperature in it, right? It's going to cause it to go up. What's going to happen to the temperature of the metal when we put it into that water? It's going to go down because it's at a higher temperature. We put it in a place where there's a less temperature, right? What's going to happen to the temperatures of the 2 objects? They're going to become the same. Okay, at some point in time. And so what is that temperature going to be? Well, let's imagine that after we dump the metal in there, okay, that the temperature of the mixture becomes, let's say, 26.4 degrees Celsius. So that's the mixture of the water and the metal. Does that make any sense that it would only go up about 3 degrees? Well, once again, I'm going to point out the fact that water has a very high heat capacity, takes a lot of energy to cause its temperature to change, whereas metals have very low heat capacities. They lose their energy pretty quickly. Okay? So this is pretty appropriate. Now, assuming that we transferred this metal to that water as quickly as possible, and why do we have to do it quickly? Well, if I just take that metal out, what's going to happen to the amount of energy that it has? It'll just start losing energy, right? To the surroundings, to the air, wherever, okay? Where we want that energy to go, here. And here's the key to the whole set of calculations that we're going to do. The amount of energy that the metal loses should be equivalent to the amount of energy that the water gains. Does that make sense? If we get that transferred over quickly enough. Okay? So, all we have to do to find the amount of, we're trying to find the heat capacity of the metal. Okay? Well, in order to find the heat capacity of the metal, I need to know its mass. Can I find the mass of the metal? By putting it on a balance, right? Just like we did our density lab. Anybody want to throw a mass out there? 92.64 grams, we'll say. Boom, we have the mass of the metal. Do we know the temperature change of the metal? Do we know its initial temperature? Do we know its final temperature? So do we have enough information to find the temperature change of the metal? Yes, we do. Do we know how much energy the metal lost to the water? No. But we can find the amount of energy that the water gained. Do we know the mass of the water? Do we know the heat capacity of water? I had it written up on the board. Does anyone remember what it was? Did anybody write that down? 4.184 joules per gram degree Celsius. Do we have enough information to find the temperature change of this water? It was originally here, now it's here. And so now we can find the amount of energy that the water gained, and because this is true, that's true. You see what I did there? And the key to the whole thing is right here. We're assuming that we get that transferred over quickly enough so that all of the energy that the metal loses goes straight to the water, and then all we have to do is figure out how much energy the water had. And that's what's going on in question number 5 here. We're trying to find the heat capacity of the metal, but we need to find the amount of energy that the metal had. Okay? So the only way we can do that is find the amount of heat that the water gained by using that information, and then transfer that value to right there. which is exactly what I did up here. And then I think I had you do the same thing in question number 6. So you can try that again. Does that look complicated? It looks intimidating, doesn't it? Does that look intimidating? How many of you followed along as I was walking through it, though? Oh, that makes sense. Oh, yeah, oh, that makes sense. Okay. So now it just comes down to a matter of practicing this stuff, okay, which I will provide that for you tomorrow. We'll practice tomorrow. That should be about the end of the period.
No. You got like 3 minutes.
Really? Good. Then let's talk about this.
No, we don't have to.
No. We're here. Let's learn.